Hello guys, let's start. So today is lecture 5.1 and it is about dimension. So to be honest, today's lecture is one of the hardest in the course. So please try really hard to understand what's going on. The proof of the main theorem today will be involved. There will be a very long lemma called Steinitz exchange lemma. If you understand that, you understand one of the major ideas in linear algebra, the idea of the dimension and the reason why such thing exists. So let's try to do it. I will try my best to explain it as clearly as I can, but just remember it is still a very confusing topic. So let me first formulate what we will prove. So our goal is the following theorem. So I will formulate a stronger statement that the statement I will be able to prove, because the one which I will formulate is really hard. It is based on some set theory ideas which we will not go into, but if you're interested, you can read about it on your own. But let me formulate it in a complete generality. So let V be a vector space over F, where F is a field. Notice it's arbitrary vector space, as large as you can imagine. Like maybe Fn, maybe polynomials, maybe something else, doesn't matter. Then, first, V has a basis. Let me denote this basis, so it is just a set of vectors. Let me say V alpha, where alpha is in some set I, namely, for every vector V in V, there exists a unique collection of indices I1 up to In in I, and unique collection of numbers xi1 and so on xin in F, such that V is a linear combination xi1 v I1 plus and so on plus xin vim. So notice I use here the second definition of a basis, which we proved is equivalent to the first one, that it is a collection of vectors, so that every vector in your vector space is a unique linear combination of those. Also notice that this collection is not necessarily finite. So when it is finite, it will be a finite dimensional vector space case, which we will talk about in detail and which will actually be the case where we will prove the theorem. But in general, it is true without any restrictions, so it is true for an arbitrary vector space. And second part of the statement is that if a collection of vectors V beta, where beta is in some set J, is another basis of V, then cardinality of I is the same as cardinality of J. So again, if vector space will be finite dimensional, this basis will be finite, and so these two numbers will be just finite numbers and they will be equal. So the statement is that for every two bases, they have the same number of elements. But if a vector space is really big, like polynomials, or even bigger, then it might happen that the set I will be infinite, and then J will have to be infinite, and this statement that they have the same cardinality means that there exists a bijection between I and J. So let me say that. So this means that there exists a bijection between I and J. So, okay, before proving that, let me give you some examples. So example 1 is the most trivial one. Let's take R2. And then, for instance, you can take a basis consisting of vector 1, 0, 0, 1, which we usually denote by E1 and E2. That's one basis. But, for instance, there is another basis, say 2, 0, 3, 1, or something like that. And one can check solving two systems of linear equations that this is also a basis, and so on and so forth. And actually, one of the exercises you have seen shows that if x1, y1 is and x2, y2 is a basis, if and only if x2, y1 minus y2, x1 is not equal to 0. So determinant of some matrix does not equal to 0, and later on you will see that absolutely similar statement holds for any Rn. So another example is our favorite space of polynomials. So V is f of x. And here it's interesting because actually we know that one of the bases is 1x, x squared, and so on. So these guys are all linearly independent. No linear combination equals to 0, and every vector is a linear combination of those. And notice it is infinite, and if you know something about infinite sets and their cardinality, it's actually countable. So, and part 2 of the theorem means that actually any other basis is countable. So there is no finite basis, no continuum size basis, every basis is countable. But another basis is, for instance, you can take 1, x minus 1, x minus 1 squared, and so on. And this is another basis, just powers of x minus 1. And it is an easy exercise that this is also a basis. We will talk about it probably during the next lecture. So, one example, second example. Okay, now let me give a crazy example. So, third example is actually quite terrible, and it is exactly the example where this cardinality, set theory, and so on arises. So let's take a field being rational numbers, and as a vector space, take real numbers. So that looks very weird, but think a little bit about it. So if you have a vector being real number, you can absolutely multiply it on a rational number, and you can add real numbers. So you can add them. This is just usual addition. And multiplication on Q is just usual multiplication on Q. So a typical example of a vector is 1 is a vector, square root of 2 is a vector, pi is a vector, e is a vector, and they are all in R. So these are all interesting vectors. And for instance, we know that, say, 1 square root of 2 are linearly independent. And this statement is just the fact that square root of 2 is irrational. If you think about it, because the statement is that there are no rational numbers, so that R1 plus R2 square root of 2 equal to 0, and this is equivalent to square root of 2 being rational. So this vector space and different questions about collections of vectors and whether they are linearly dependent or not is basically number theoretic domain. Questions here are very hard. For instance, if you start to ask questions like whether P and E are linearly independent and so on, you very quickly come to things nobody knows how to prove. Anyways, that's a vector space. And if you think what is a basis here, so a basis will be some crazy collection of real numbers, so that every real number is sum of several of those, and no linear combination of any of them equals to 0. So there is no way to sum up real numbers with rational coefficients to get 0. So for instance, you can take 1 but no other rational number. Then you can take square root of 2 but no other number of type a plus b square root of 2. So nothing like that, and so on. And the statement is that there is some crazy collection of numbers so that it will have this property. So notice that if you think a little bit about it, if you know cardinalities, you will see that this basis will have countable cardinality. So there is no way one can write down one without what's called using axiom of choice. And actually, the proof of this theorem in complete generality requires axiom of choice. So you need some set theory, you need what's called Zorn's lemma, and then it becomes a simple exercise. In this course, we will be not dealing with these crazy examples, and even such example as polynomials with countable bases will be a little bit beyond what we will talk about, though it is not much harder. So I will restrict myself to the case when V has a finite basis. So when V has a finite basis, of course we want to characterize it in some way so that both parts of the theorem will be staying meaningful. So the correct way to say is that we will look at the case when a vector space is finitely generated. So we will prove that a vector space which is finitely generated has a basis, and this basis is finite, and every two bases have the same cardinality. So this will cover cases like R2, Rn, Fn, polynomials of degree less or equal than something, and many other examples. Okay, so next part. So now we actually start proving things, and I want to start with theorem, which will be called theorem 1. And theorem 1 is the following statement. So sorry, I have a cat playing with my only pen. Cat, give it to me. Give it to me. Oh, sorry. Yes. Okay, theorem 1. So theorem 1, let V be a finitely generated vector space over F. Then V has a finite basis. So notice the difference between this theorem and the more general statement I formulated a few minutes ago is that here I assume V is finitely generated, and that's what guarantees me that I will have a finite basis. So basis of finite cardinality. So in previous statement it will be cardinality of the set I is finite. So set I consists of a bunch of finite number of vectors. Okay, so proof. So remember, there was an idea that if you have a subset of positive integers which is not empty, it will always have the smallest element, minimal element. So I told you that this statement is equivalent to induction axiom of integer numbers. So we will use exactly that. So consider a set which I will denote by, I don't even know, B. No, yeah, B. Consisting of numbers n such that V is generated by certain n vectors. So there exists a collection of n vectors which generate V. So we know that B is of course a subset of n, just because, you know, these numbers are 1, 2, 3, 4, 5, maybe 0 as well, and if B is not empty. Definitely it is not empty because V is finitely generated. So there exists a finite collection of vectors which generated, so there exists some element, some number n inside B. So then B has a minimal element. Let's call it, for instance, M. So, vectors, there exist vectors v1 up to vm such that v is a span of this collection of vectors. And for any smaller numbers than m, such collection does not exist. So let's prove. So claim is that v1 and so on vm is a basis of v. So let's prove the claim now. So of course we need to show that v1 up to vm are linearly independent. So we need to show that they are linearly independent because that's the only thing. So they already generate v, so if they are linearly independent, then they form a basis. So suppose not. Prove from the contrary. Not. Then remember there was a statement that if a collection of vectors is not linearly independent, one is a linear combination of the other. So then there exists I from 1 to m such that vi equals to alpha 1 v1 plus and so on. Then we omit vi term up to alpha m vm. So some vi is a linear combination of other vectors, and then without loss of generality we can assume that this I just equals to m. So of course it can happen that this I does not equal to m, but then just relabel the vectors and continue the proof. So it absolutely does not matter which vector in the collection is the linear combination of others. So we can assume it's m just because it will be a little bit more convenient from the perspective of the notation. So okay, then sets vectors v1 up to vm minus 1 generate v. So of course this cannot happen because we know that v is a span of v1 and so on vm, and m is a minimal such number. So here there will be a contradiction. Let's show why this is actually follows from the fact that they are not linearly independent. So indeed for v in v there exist some numbers x1 up to xm such that v equals x1 v1 plus and so on plus xm vm. But then you can use this formula for vm to simplify it and just plugging in instead of vm alpha 1 v1 and so on, we see that it equals to x1 plus alpha 1 v1 plus and so on plus xm minus 1 plus alpha m minus 1 vm minus 1. So every vector, so for every vector in v, v is inside the span of these vectors v1 up to vm minus 1. But then, so m is not equal to the minimum of elements in the set B, and that's a contradiction. So that proves the claim, and the claim what this guy is a basis, so a vector space has a basis, and that proves the theorem for us. So again, let me explain what happened here. So we have a vector space, and I wanted to prove that it has a basis. So we took the minimal size set of vectors which generate v. And then I proved that it is linearly independent. The set is linearly independent. If not, find the vector which is linear combination of others, and then you don't need it. So even if you omit it, you will still get a generating set. and this contradicts the minimality of this M. So here is another perspective. So let me just draw a picture here. So suppose you have a bunch of vectors in R. You want to prove the theorem for R2. So you have, I don't know, 5 vectors of R2. And then you want to show that R2 has a basis. And then you just start to omit the vectors. So we know that this is linear combination of the others. We can forget it. And then this is a linear combination of others. And then this is a linear combination of others. And then you should be careful because this one is not linear combination of other two because these two are proportional. So you cannot forget that. But this one is linear combination of others. And so you can forget this one, for instance. And here you come to a basis. So every collection of vectors which generate V contains some basis. That's actually an important corollary of the statement. Maybe even let me just say that. So the proof is absolutely the same. So maybe remark every generating set of V contains a basis. And you prove it just in the following way. You take a generating set. If it is not a basis, you can take one of the vectors. And then if you forget it, you still get a generating set, and so on and so on and so on. You continue until you have to stop. So that's an important corollary from the proof, maybe. So remember that, please, as well.